So thank you very much. So I would like to thank the organizers of the session for the invitation to talk today. And so as mentioned, I will talk about the role of land forcings and feedbacks in the attribution of climate extremes. And I would like to acknowledge my co-authors who are group members at ETH Zurich. So I often show this figure, which is looking at the role of oceans versus land for the climate system. And obviously, we have impacts of the ocean on the atmosphere and also impacts of land on the atmosphere. However, we should remember that we are living on land, we are living on continents. And so actually, if we want to predict climate on land, land feedbacks are actually quite significant in terms of constraining climate over the continents. Just as an illustration, I'm showing here some results from this study, which was published earlier this year, Nature Climate Change, where we are looking at trends in temperature extremes over land. And as you know, there was a hiatus period if you are looking at the global mean temperature. But if you are looking at temperature extremes, actually you see that there was a continued increase of those temperature extremes over land. So basically, we need to understand regional processes if we want to be able to predict those processes. For instance, here you see that if you were to try and predict the regional temperature from the global mean temperature, you would not be able to. So there is a range of processes on land which affect the atmosphere. I will only talk about two main aspects. On the first part about the impact of evaporative cooling, so the extent to which when you have dry conditions, this affects evapotranspiration and as a result in temperature. And in the second part, I will talk also about possible impact of albedo on temperature extreme. So I often show this figure regarding the interaction between soil moisture and the partitioning of net energy between the latent and sensible heat flux. So basically the tendency looks more or less like this. If you have wet conditions, you basically don't have any sensitivity of latent heat flux on soil moisture. Then you have a transitional climate regime here, where basically the latent heat flux is very much... Anyway, so basically you have much of an impact of soil moisture on latent heat flux in this transitional climate regime. And just to illustrate the possible impact on temperature, so in the transitional climate regime, you have more or less this situation, which means that you have a very high variability of the latent and sensible heat flux as a function of soil moisture content, and as a result also a strong impact on temperature variability. We had a study on this a long time ago in 2006, which were looking at the possible impact of soil moisture temperature feedback in the context of climate change projection. Here you see the temperature variability in Europe in a fully coupled simulation, regional climate simulation. And that's what you get if you prescribe soil moisture to the climatology. Basically, much of this variability is removed. It's actually about 60% of the variability is due to soil moisture variability. These results were recently confirmed from a multimodal experiment for the CEMIP5 projections. I don't have time to present those results, but if you're interested, you can check this study in GRL, which I presented on Monday. Now, what we have done in recent years within our group was to try and constrain those relationships from observation. So what I've shown before were results from models. And these are some examples. So this is a study for Southeastern Europe looking at the correlation between the percentage of hot days and precipitation deficits. And that's basically for transitional regions, so one region where we would expect that moisture availability is very important for the occurrence of hot extremes. What you see is that indeed you have a high number of hot extremes only when you have dry conditions before. So it suggests that indeed moisture availability is important for the occurrence of hot extremes. And more recently we had a study led by Brigitte Müller, which looked at this on the global scale. And this is looking at the probability of having an above average number of hot days after respectively dry versus wet conditions based on precipitation index. And you see that in a range of regions, so not only in Southeastern Europe, but also in range of other regions in mid-latitude, both on the northern and southern hemisphere, you basically see a relationship. So basically, in those regions, you tend to have a probability of 60 to 80% of having an above average number of hot days after dry conditions, and actually only a probability of about 30 to 40% after wet conditions. This is obviously very important for forecasting, but also for attribution, because this means that if you have an event, an extreme temperature event occurring, basically part of the explanation would be linked to moisture availability, and then So basically, the underlying mechanism need to be attributed then to external forcing or internal climate variability. More recently, what I was showing before was basically a relationship between the number of hot days or the probability of having a hot day and moisture availability. More recently, we also looked at possible impact on the intensity of temperature, which is of course also relevant for impact. And these are on the left results based on models, so the glass SMF5 experiment. This is based on observation. And actually, we were quite interested to see that you have a non-linear effect if you're looking at the number of hot days because of a threshold effect. But if you look at the impact on intensity, it's mostly a linear relationship. So we think from this we could derive a linear scaling of absolute temperature extremes with some moisture availability, and that's a topic we are currently working on. So this was the main result I wanted to show in terms of the possible impact of some moisture temperature feedback for temperature extremes. And now I want to say a few words about droughts and also impact of land albedo. So this is a study which we recently published earlier this year, which is led by Peter Greve, a PhD student in our group. And he looked at basically robust trends in droughts over continents using a range of observational data sets, from precipitation, potential evaporation, and actual evapotranspiration. What he did was basically we have a large uncertainty in all of those data sets. So we need first to establish what are the combination of data sets which are more realistic. So to establish this, he used a classical hydrological framework from Budico to assess which combination were most realistic. So I cannot go into the detail, but it's described in the paper. So from the results, basically looking now at the most realistic combination, we get the following robust trends in moisture availability on land. What you see on the top, first is that there are very few regions with robust change. So we're looking at the difference between 48 to 68 and 85 to 2005. So in many regions, actually, you don't have any robust change. But you see that some regions, so in red shows basically main drying. I cannot go into the detail, but red is mostly drying, blue is mostly wettening. And so you see that there has been some tendency for drying, for instance, in Africa and Europe, and some wettening trends in the Americas. But actually, this doesn't really support a commonly heard paradigm, which is saying that dry regions would be getting drier and wet regions getting wetter. So for instance, you also don't see really latitudinal changes. You don't really see that all drying regions are found in the same latitude. This is also confirmed if you do a specific analysis by climate regime, which is provided here. So basically, those regions where the dry gets drier, wet gets wetter paradigm is confirmed as those regions in red to blue. And the other region where it's invalid are shown with the other color. And as you can see, actually, there are less regions where this paradigm is valid and regions where it's invalid. And one main reason is that this paradigm was based on ocean results. So if you look at ocean data, you find that saline regions become more saline, and less saline regions become even less saline, but these trends do not apply over land. And just to come back to this point, I think part of the misconception can also come from analysis when you're looking at trends in P-E on global scale. And so a well-known study from Held and Soder, but which was basically for the global scale. So this is the P-E by latitudes here. And that's a change in P-E for the future. And so there is this well-known behavior, if you look at the average on the globe, that basically regions where you have a positive P-E show a tendency towards even a further increase in P-E. Regions with negative P-E show a tendency to a decrease in P-E. But that's for the whole globe, and also if you look at ocean-only response. But if you look at the land, so the continents, you see that the behavior is very different. So in terms of attribution, this means that looking at past trend in droughts is quite complex, and it's not easy to, for instance, assume that if you have a dry region that you've had a stronger drought, that this might be related to climate change forcing. So I finish with the possible role of land surface processing, surface processes related to albedo. And basically, so land albedo can be changed through a range of forcing, for instance, land cover changes, also changes in land management. That's one example. So if you have agriculture area, you can have different type of management. And if you have no-till farming, this would leave some residues on the soil of the crops, and this affects the albedo. And this is one site in France which is showing the difference in albedo. At one site with conventional tillage, and then when you don't have any tillage. the total effect is of the order of 0.1. Now, Edward Davin in our group looked at the possible impact of this change in albedo in regional climate simulation for Europe. And that's the result here for Northern Europe. So, of course, you would expect that if you have an increase in albedo, on average, you would get a decrease of the temperature, which is what we found. But what we were more interested in was possible impact on the temperature distribution. And so this is what is shown here. That's basically the difference in temperature as a function of the quantile. So if you look at Q50, that's for the median. So you see for the median, it's about a decrease of 1 degree. But if you lose at very high temperatures, the total effect is of the order of 2 degrees. So you basically get an asymmetric response to this albedo forcing, which suggests that there is a preferential cooling of warmer extremes from surface albedo forcing. So I come to the conclusions. Land surface processes and land atmosphere interaction play an important role for temperature extremes and droughts, as I've shown. And really the important aspect is that they can induce effects which impact extremes differently from the mean, so as I've shown for albedo, and also that they affect regional processes differently from the global mean change in the climate system. And so this is quite important for attribution, because this means first that we need to really fully understand the mechanism and also validate them in model when models are used for attribution. And this means also that it's relevant for the assessment of the contribution of internal climate variability versus external forcing for respective events. Thank you.
We have time for questions. Any questions for Sonia?